Yeah, so it's a pleasure to be back at NICE, even if only virtually. And the topic I want to talk about is the simulation of SNNs as discrete event systems. And this really started as a hobby project, but I think it's actually quite relevant for neuromorphic computing. And so despite the fact that it's still a bit work in progress, I'm happy to share it here. So let me start at the beginning. And I want to start with the question how neurons even compute, in particular spiking neurons. And this question is a bit difficult to answer because, well, you need to find a good level of abstraction to model this. And as we are all familiar with, the most detailed biophysical models of neurons, like the Hodgkin-Huxley model or the RAL model, they're really good at capturing the biological properties of the neurons. But of course, they are quite detailed, which makes it difficult to simulate large networks. They are expensive to simulate at scale. And that also means it's difficult to really understand if they solve a problem, how exactly they do it. And I think this is the reason why most of the field in neuromorphic computing and SNNs in general has moved on to neural models that simplify these neural dynamics quite a bit, such as the leak integrated fire neuron, adaptive exponential model, and so on. And these models are great for computational modeling because they retain a lot of the important features of the biological models, but they reduce them in substantial ways and throw out a lot of details that we might not be interested in, like the exact shape of spikes that are generated and so on. And that means that it becomes possible to simulate fairly large networks of leak integrated fire neurons. And as you have seen throughout the conference, there are really great ways to train these networks, and new learning rules are being discovered all the time, how to get the most performance out of these networks. However, there's one drawback, at least for me personally, I see it as a drawback, that when it comes to explaining how these networks actually do computation, the mental model that most people refer to is really the concept of function approximation, which is the same framework that deep learning and reservoir computing use. And I always see this as a bit of a drawback to explain spiking neural networks. Now, this is, of course, not the only way how you can explain computation. So there are a bunch of other approaches, and a lot of them were already talked about in this conference and other talks. And the thing I really want to focus on is the idea of describing computation as much as possible in event-driven way. And I want to motivate this actually from a biology side, because if you go through the literature and you see how people actually talk about the behavior of neurons, then you often find also statements like this one here. This is from a paper from 96, where the authors argue that spiking neurons do a lot of coincidence detection. And maybe the temporal integration is one feature of the neurons, but it's maybe not the only interesting property. And the reason I find this interesting is if we really care about coincidence detection primarily, we don't need to even model the dynamics of the neurons in any sort of detail. There are much simpler models from computer science that you can also use to capture this qualitative behavior, such as finite state machines or Petri networks. And so I'm interested in using these sort of models to model spiking behavior. And I assume that Petri nets are probably not familiar for everyone. So I want to give a 1-minute crash course here, very high level. So what you see here is a picture of how you could represent a stochastic synapse in one of these time Petri networks. And it's composed of different blocks here. So you see places that are shown as circles here, and each place can hold a number of tokens that are shown by these black dots here. And in between these places, you have transitions. And these transitions, they can take tokens from some places and they can add tokens to other places. And this models basically transition of states by moving around tokens. And a specialty of time Petri networks is that you can add timing constraints to these transitions. And so in this case, for example, the timing constraint is used to show how long it would take a synapse to turn off again. So effectively modeling the duration of an EPSP that this synapse would trigger. Now, if this is the model that you use to describe synapse, then the entire state of the system is described by what's called a marking. And it's basically consists of two parts. It's the assignment of tokens to places and the assignments of counter values for the different transitions. And that's all that you need to understand basically these Petri networks. But this is quite abstract, so I want to walk you through a very brief example. What happens at a synapse now, this type of model, if you would trigger it with a spike. So in the first example that I want to show here, the synapse starts in an off state. And now at some point in time, it receives a spiking input. And now the synapse has a choice whether it will fire or not. And in this example, the synapse chooses not to fire, which is random in this case. And as a result of this, the incoming spike doesn't have any effect and the synapse reverts back to the original state. In the second example, a spike arrives, but this time the other transition, the start transition, is chosen, which means the synapse will now turn on and start an EPSP. And what that means is the state of the synapse will go from the off state to the on state, and that immediately triggers a countdown timer, which just tracks the remaining time of this EPSP. And once the time is up, the timeout condition is reached, and the synapse will reset through the stop transition and then go back to the initial state. So what I want to show here is just that with these sort of models, it is actually possible to model time behavior over time in a discrete state system. And the same concept that I showed here for a synapse, you can also use to model arbitrary other parts of neural networks. So you can model dendrite segments or neurons out of this. And by extension, that means if you want to, you can build entire SNNs based on this framework that really capture the behavior of the SNN in a purely event-driven way. And what I like about this is that you can capture some qualitative features of the biological networks you might be interested in, like, for example, coincidence detection, while leaving out all of the implementation details, including even membrane potential dynamics. And that means the resulting models are fairly efficient to simulate because they only use basically integer states. But more importantly, what I find really interesting is that this gives a completely different explanation of what it means to do computation in such a spiking neural network, because now computation is really equivalent to state transitions. And that is the notion of computation that also Turing used for the Turing machine originally. So it allows us to tie it in a bit with concepts from computer science. And I wanted to drive this point home, so I was thinking about what would be a good example, and I went down a bit of a rabbit hole. So I wrote a script that takes a simple Turing machine. So in this case, it's a counter machine, which is a very simple representation of a Turing machine, with a program here that consists of 13 instructions. So each counter can be incremented or decremented, and there's looping conditions. And I turned this into an SNN. And this SNN can then be translated into a Petri network, and this Petri network can then be simulated. And what you see here is a little video of that. Don't try too hard to make sense of it. So I have to say this is also a bit work in progress, and I was debugging this until recently. But the point I'm trying to make is that it's possible with this sort of framework to build fairly complex systems that have complex behavior without invoking the concept of differential equations at all. So you stay completely in this event-driven world here. And so for interest of time, I cannot go into much detail here. But the main, I think, part that interested me about this is that a network like this, which does a fairly complicated task, actually just requires, in this case, 43 slightly complex neurons here. So, of course, the idea to simulate spiking neural networks, I mean, building an example like this, like a Turing machine, is just a toy example. But the vision that I think where this might lead, hopefully, is to build a more useful framework for constructing spike-driven neuromorphic systems. And I think this requires 4 major building blocks, and 2 of them you already saw a little bit of. The first one is we need to construct models of each of the atomic building blocks that make up these networks, like synapses and neurons. And then we need to be able to simulate these models efficiently. And what you saw right now is something that I hacked together, but I'm working on a slightly more sophisticated simulator for this. And then ultimately, in order to build something useful with it, we would need some way to implement more complex behavior. So there needs to be some higher level description language that would allow to compose useful neuromorphic systems out of this. And ultimately, this could be used if you combine it with really neuromorphic circuit implementations of each of the building blocks to synthesize kind of complex behaviors from kind of a user convenient high-level representation. So this is a lot of work to be done, and it's all very much work in progress. But if you're interested, you can reach me here. Here's some contact information. And with that, I'd like to close and answer any questions you might have.